Immunohistochemistry is a powerful tool in forensic pathology, but it has specific strengths and limitations we must understand. It allows us to confirm the presence or absence of specific proteins in tissue, offering molecular level insights. However, IHC is not a magic bullet. Its utility depends heavily on proper technique and careful interpretation. We'll explore how IHC fundamentally differs from traditional histochemical stains and what that means for forensic investigations. IHC fundamentally shifts our approach from a general chemical reaction to a highly targeted molecular search. Unlike a histochemical stain that reacts with a broad class of molecules, IHC uses antibodies to pinpoint a single protein. This specificity is its greatest advantage, allowing us to identify subtle changes or specific cell types that would otherwise be invisible. But this precision also means we need to be acutely aware of potential pitfalls, like antibody cross-reactivity or nonspecific binding. We'll see how this targeted approach opens new avenues for forensic investigations. Building on IHC's precision, we can use it to estimate the age of an injury, a critical aspect in forensic cases. The body's response to injury unfolds over time, with different proteins appearing or disappearing at predictable intervals. By staining for these specific markers, we can establish a timeline for when an injury occurred. This is a significant leap beyond what gross examination or even routine H&E can provide. We're now going to look at a specific example of how IHC reveals early cardiac ischemia. So IHC's ability to detect early changes is particularly vital in cases of cardiac ischemia, where it can reveal damage long before H&E. Grossly, a heart attack might not be visible for hours, and even H&E can miss early signs. However, IHC can detect early markers like myoglobulin loss or complement activation within minutes to a few hours of ischemia. This allows us to confirm a heart attack as the cause of death even when other methods fail. And this same principle applies to other types of injuries, as we'll see next with head trauma. So extending this concept to head injuries, beta-APP staining provides definitive proof of a survival interval after trauma. Beta-amyloid precursor protein, or beta-APP, accumulates in injured axons within hours of a traumatic brain injury. If beta-APP staining is positive, it confirms the individual survived for at least a few hours after the injury, which is crucial for reconstructing events. This molecular evidence can differentiate between an injury sustained immediately before death and one that occurred earlier. However, the longer the postmortem interval, the more challenging these interpretations become. We just saw how IHC can reveal subtle changes like beta-APP in head injury, but there's a critical caveat, the postmortem interval. The longer the time between death and tissue collection, the less you can trust a negative IHC result. Autolysis degrades proteins, meaning the target antigen might simply no longer be there. So a negative stain doesn't necessarily mean the condition wasn't present. It might just mean the tissue is too degraded to show it. This is especially true for highly labile proteins. And that brings us to another challenge. Fixation itself can sometimes be the problem. Building on the idea of tissue degradation, sometimes the very process we use to preserve tissue can hide what we're looking for. Fixation, particularly with formalin, cross-links proteins. This can mask the epitope, the specific part of the antigen that the antibody recognizes. So, even if the protein is present and intact, the antibody can't bind to it. This is why antigen retrieval techniques are so crucial in IHC. We're essentially unmasking those epitopes so the antibody can do its job. But even with retrieval, some antigens remain stubbornly hidden. And sometimes what looks like a signal isn't a signal at all. This slide highlights a fundamental issue in IHC. A brown stain doesn't automatically mean a positive result. Nonspecific binding of the antibody, endogenous peroxidase activity, or even melanin can all produce a brown color. You need to be able to differentiate true specific staining from background noise. Understanding the expected localization of your target protein is key here. Is it nuclear, cytoplasmic, or membranous? If the brown is everywhere, it's probably not specific. This is where proper controls become absolutely non-negotiable. Following on from the last point, without proper controls, a positive IHC result is just a brown stain. You can't interpret it. Positive controls confirm that your reagents are working and that the antigen is detectable in appropriate tissue. Negative controls using an irrelevant antibody or no primary antibody help you identify nonspecific binding and background staining. These controls are your benchmarks for specificity and sensitivity. They are the scientific foundation for interpreting your results. And, ultimately, they ensure the power of IHC is harnessed responsibly. So, we've covered some significant challenges, so postmortem interval, fixation artifacts, and the ever-present risk of nonspecific staining. But despite these hurdles, IHC remains an incredibly powerful tool in forensic histopathology. It allows us to detect subtle changes, confirm diagnoses, and provide crucial timing information. But its power is directly proportional to the discipline with which it's applied. That means meticulous technique, rigorous quality control, and a deep understanding of its limitations. When used with this discipline, IHC provides invaluable insights that gross examination alone cannot. This is the essence of responsible forensic practice. Thanks.